Hi, welcome to Team Swarms. I would like to introduce our team, which consists of Andrew Holmes, Scott Jordan, and Daniel Elias, which are all electrical engineering majors, as well as Connor Gross and Roderick Thomas, which are computer engineering majors. Our electrical engineers focus mainly on the design and maintenance of our hardware, as well as testing and validating the integrated systems. And our computer engineers formulated algorithms for our software interface, as well as image recognition integration. All members of our team assisted in every phase of our project, in which we all gained knowledge in both aspects of electrical and computer engineering. Now I want to discuss the concept of our project idea, swarm robotics. The concept of swarm robotics is based on the basis of grouping multiple robots or devices to perform a desired task. Swarm robotics is a new approach to the coordination of multi-robot systems, which consist of large numbers but of mostly simply physical robots. In our case, we use 2 to 3 robots that can be scaled to a large number of bots using the same control architecture and design aspect that we prepared. The idea of swarm optimization has actually been around for a few decades now, and our idea is to implement this concept funneled from basis of fact. Fact is, sometimes it is impossible to complete a task by a single person. In such cases, there's a need of a team or a group of members that can collaboratively work and make the job easier. Our motivation behind this development is that our design and algorithms should be able to be implemented and optimized for a small or large scale automated warehouse management system, which could consist of hundreds of swarm bots completing a variety of given tasks. Now, Daniel will introduce some of the strengths and weaknesses we observed throughout the semester when developing and testing our system.
Thank you, Andrew. Our project had various strengths and weaknesses which were explored throughout the semester. Some of the key strengths of the project were the robust framework of the robots. Also, the adaptability of the robots, meaning that they can be inserted or deleted from the environment with no requirement to change the task operation. Another key feature was the scalability of the project because the control architecture of each robot is the same, no matter the number of robots. Some of the various weaknesses explored throughout the semester were the area of camera view, which is roughly 20 square feet, making it difficult to run more than 2 robots with multiple objects without a clutter effect. Along with the area of camera view was the camera's resolution, the remote working, the collision avoidance, the target ID assigning, the steering efficiency, and the computing processing power. Next up is Rod, who will be talking about the quantifiable data and constraints.
Thank you, Daniel. We have some quantifiable data that we wanted to test. This includes the time it takes to complete moving numbers of items to the trash area, the success rate for number of robots versus the number of bots in the play area. Sometimes the play area needs some human intervention because of the bounds, and there are edge cases that involve human intervention, so we did keep track of that also. Next, we have the number of bots that can be in the play area, and finally, the number of boxes that can be moved to the trash. With that being said, we did some test trials to test our prototypes. I'm not going to go through all of our tests. However, our fastest average time of completion was 35.6 seconds, which was the 2 robots and 2 boxes, and only needed 1 human interaction out of 3 runs. Our slowest average time was 1 minute and 17 seconds, and this was the 2 robots and 5 boxes with a total of 3 human interactions. To conclude, we had some constraints on the size of the play area, which limited the number of robots and boxes for the best results. Another one of our constraints was the camera view and the resolution, and boxes getting pushed into spots where the robot can't get to. Now I am passing it on to Scott to talk about the hardware.
All right, thank you, Rod. Our robot was based off of the Pioneer design with 2 wheels and a ball bearing as the third point of contact on the ground. The chassis and bumper and wheels were 3D printed. For power, we're using a rechargeable 9-volt battery with a buck converter giving us a steady 5 volts. The motors on the sides are FS90R continuous servos, and the brains are an ESP32, giving us Wi-Fi connectivity to talk to our Raspberry Pi 4 mounted to the ceiling. It is running an instance of OpenCV in Python and grabbing images of the entire play area from a generic Logitech USB webcam. And now I'm going to pass it over to Connor, and he'll talk about the subsystems that are running.
Thanks, Scott. So as Scott mentioned, I'm going to be giving a high-level overview of the various subsystems that make up our final project design. In addition, I'll give a very basic introduction as to how they all work together and play together. So the first main subsystem that we had to work on was the vision subsystem. So like Scott mentioned, we have a Logitech camera sitting above the play area, and that is constantly taking video of the play area below it and sending information to the rest of our system using OpenCV as the tool to help guide that. The next subsystem that we're going to talk about is the routing subsystem. This one was incredibly important for the overall success of our project, as it was the driving force behind the information being sent to the robots to be able to move around the space and interact with the boxes in real time. And then the last subsystem that we're going to talk about is the basic movement subsystem. The movement subsystem relies heavily on a lot of the focuses of the hardware that Scott mentioned, and these all play together in order to achieve our original goal of taking robots and taking boxes in a play area and using those robots to move the boxes into the trash. So the basic flow of all of these subsystems together will always start with our vision system. The camera will be constantly taking live video every single frame that it possibly can. And every single frame, it will pick up on the Aruco markers that you will see on our robots, and as well as on the boxes. These markers will then give more information that the routing engine will then use to create the pathing as well as angle and directional control that is needed. Finally, all this information will then be compiled and sent to the robots to help complete the subsystem cycle with our movement, driving those robots toward those boxes and finally driving them towards the trash. This has been the complete and total overview of our design, as well as everything else about the Swarm team. Thank you very much.
Now I will give a brief demonstration of these subsystems working together to route our bot through the play area. To begin, each bot is placed in the play area where it routes to its home position, which is denoted by the 3 white circles in the bottom left of the play area. As the box is placed, a bot is paired with it, noted by the number above the bot and the box. That is the target ID value that holds the ID of the object that it is paired with. Once paired, the bot routes to the push point of the box, defined by the cyan radius on the edge of the box opposite the trash. Once within this radius, the bot routes to the trash, pushing the box with it. If the bot slips out of the push point, routing is reverted to targeting the push point. To prevent the bot from accidentally pushing the bot away from the trash while moving to the push point, a repulsion radius is generated to cover all edges except the push side with the push point. If the bot enters this repulsion radius, it begins routing to the center of that radius, albeit with inverted steering so it can return to normal operation and routing to the push point sooner. Once the box enters the trash zone, it is unpaired from the bot and removed from pairing eligibility. If there is still an unpaired box in the play area, the bot will pair to it and route to its push point to start the functional loop again. If not, it returns to its home position.